universe, there are three main common forces of attraction. The first is the electrostatic attraction, which is the attraction between positively charged substances and negatively charged substances. Then we have the magnetic force of attraction. And similar to the electrostatic force of attraction, you got the attraction of the south end of a magnet to the north end of a magnet, which really has to do with the distribution of electrons inside that magnetic bar. So it's almost like a positive and a negative. And then you have the gravitational force of attraction, which is the force of attraction that objects exert on each other in order to kind of reel each other in. Now, on planet Earth, we are attracted to its core. So when you drop something, because we stand on the surface of the Earth, and the core is below us, or the center of the Earth is below us, everything falls down. But what happens when we go out into outer space and things are not really above or below each other, but they're sort of to the side? Then the gravitational force moves laterally and not vertically. The force of gravitation is the forces that each mass exerts on another mass from the center. So from one center of a mass to another center, they are bringing each other in. And the reason why this happens has nothing to do with charges like the magnetic and electrostatic forces, but has to do with the dips that they create in time and space. But that's for a whole other video. Even more so, or adding to the complexity of that, the farther you are away from the center of mass, the less gravity has on you, or the less effect the gravitational pull is on you. And so we can approximate just how much gravity something is experiencing based on the mass and how far it is from the center of mass that is pulling. Now, to calculate the force of attraction between two masses at a set distance is given by this formula. Fg is equal to large G, which refers to the Cavendish constant of 6.67 times 10 to the negative 11, with a whole lot of units there. And then the R represents the distance between the masses. So it's proportional to the distance squared. And like we've written over here, it's between center to center, not the edge of each mass or at the beginning of each mass, but from the center of one mass to the center of the other. So we got two gravitational formulas or force of gravity formulas that we see commonly used in physics. The question is, how do I know which one to use? Do I use the more simple version of Fg is equal to m times g? Or do I use Newton's universal law of gravitation formula? The quick, most immediate way to decide is to look at the radius question here. And what I mean by that is that if distance is given, then we want to use the universal law of gravitation, this one. Now, this formula over here would be when the objects are so close that it's not even worth mentioning the distance between the two, or the distance is negligent. So if distance isn't mentioned, use this formula here. But if distance is mentioned, then of course we have to use the universal law of gravity. So looking at our first example here, it says, what gravitational force does the moon produce on the Earth if their centers are 3.88 times 10 to the 8 meters apart? The moon has a mass of 7.34 times 10 to the 22 kilograms, and the Earth has a mass of 5.98 times 10 to the 24 kilograms, and these are, of course, approximate numbers. Now, the distance apart, remember, from center to center, that is going to be our R value, okay? So, in this case, we really just want the force of gravity that the moon exerts on the Earth. So we're going to use Newton's formula over here. And it doesn't matter which one you would label as M1 and M2. I tend to make the bigger mass M1 and the smaller mass M2, but it really doesn't matter. So I wrote this one out in fully expanded form because I want you to see how the units will cancel out to give us a Newton right? Because forces are measured in newtons. But I won't always be given all the units in the Cavendish value here, the large G value. So we can see here that the kilograms are all going to cancel out since this is under the denominator. Okay. And then, so not all of them going to cancel out, I should say. Sorry, remember that this would make kilograms squared. So one of those kilograms would cancel out. And you'd be left with kilograms. And as well a meters cubed for now. So the units that we're left with here, after we do all the calculations, it's meters cubed times kilograms per meter squared times second squared. So again, the meters here are going to cancel or simplify, and then we end up getting kilograms times meters per second squared, and that is equal to a newton. So essentially it's 1.94 times 10 to the 20 newtons. So for the next question, let's increase the complexity a little bit here. What is the force of gravity acting on a 70 kg astronaut who is at an altitude of 6.38 times 10 to the 6 meters? So what I'm going to do is I'm going to draw the actual apparatus that we have here. So let's say that this is the Earth. Okay, so I'll write E for Earth. And then over here, we have our little astronaut. Okay, I'm going to... This is not to scale, okay? And actually otherwise that's a really big person. But let's say I have an astronaut over here, okay, who happens to be, so the distance here is 6.38 times 10 to the 6 meters. Now remember, gravity is from center to center. So if the center of the Earth is here and the person's center is here, then the actual distance, or the R value, is this. So you'd have whatever this is plus the radius of the Earth. Well, the radius of the Earth, as would be commonly given, I'm going to write RE here. That would be also 6.38 times 10 to the 6 meters. So your entire R value is this whole distance over here, and we have to keep that in mind when we're calculating this. Now, because distance is given, we know we have to use the universal law of gravity formula from Newton. So plugging in all the variables here, we're going to put the Cavendish constant. And again, I'm going to do it without the units this time because we know now that they do cancel out properly. And we're going to use the mass of the Earth, which again is a constant that's going to be given to you at 5.98 times 10 to the 24 kilograms multiplied by the mass of the astronaut. Okay, and then we're going to divide that by, and this is the part of the question here that some people would miss. So we're going to add these two together, right? Because the Earth's radius itself is 6.38 times 10 to the 6, and the astronaut happens to be orbiting 6.38 times 10 to the 6 above the atmosphere. So we're going to write 6.38 times 10 to the 6 plus 6.38 times 10 to the 6, and then that is all going to be to the exponent 2. So after plugging that in, you're going to get a force of gravity exerted on the astronaut of about 171 newtons. So for our third example, and again, we're amping up the complexity here of these problems. An astronaut weighs, I'm going to highlight that word weighs, 800 newtons on planet X. So remember, we don't know, we can't assume any radiuses of the Earth or masses. This is planet X, it's unknown. How much would he or she weigh? So again, we're asking for a force of gravity if they were at an altitude equal to the radius of X above the atmosphere. So let's draw how that would actually look like first. Okay, because sometimes I find it's easier to envision it. So I got planet X here. And let's say the radius here is given a value of A. Okay. Whatever that value of A is, your astronaut is A above, kind of hanging out above at that distance. So what you could say is that your radius is equal to 2 times a. So whatever the entire distance between the astronaut and planet X. So when we plug in our value for the radius between the two objects, is going to be double what the radius of the planet alone is. So how does that translate? Well, remember that the formula is as follows. Since distance is measured or mentioned, we know that we're going to use the universal law of gravitation. That includes or accounts for, I should say, the distance between the two masses. Another thing, though, that's going to help us in solving this problem is to remember that the force of gravity or a force of attraction is equal to the weight. It's the same thing. So what we're going to write here first is we're going to write 800 newtons, right? Because that's how much they weigh on planet X. 800 newtons is equal to G multiplied by m1 times m2 over r squared. And what we're going to do from here is we're going to do exactly what the question describes to us, or kind of shows or tells us what's actually happening. We're going to say that 800 newtons is equal to gm1, m2. We're given no other variables, but we know that the total radius, or the distance between the astronaut and the center, is going to be double. So whatever the radius of the planet was, it's going to be 2r and then squared. And that's going to be significant because when we plug in this here, that would give us 800 newtons is equal to g m1 m2, and if I expand the square, that's going to give us 4r squared. And what you do to one side, in this case divided by 4, you must also do to the other side. So that 800 newtons is also going to be divided by 4. And so 800 divided by 4 is going to give us a force of gravity of 200 newtons. So this is really a left side equals right side question, and what you have to remember to do is any changes you make to one of the sides, you have to make the same changes to the other side. That way we're not creating a false statement.